was cute. What do you see on the screen, guys? Yeah. How many of these did you already know? All the 1 over ones? We've talked a little bit about it, but technically last section we just did like 1 over x and 1 over y. We didn't say that cosecant was 1 over sine, even though sine was y. We didn't say that secant was 1 over cosine, even though it was 1 over x. Now I said it, I'm almost positive, a few times. Some of you guys said it multiple times. But the formulas that we wrote down didn't say it. In this section, you do get introduced to something. And now this is just a little basic, very short, sweet introduction to these fundamental identities. Way more identities are coming in Chapter 5. But, oh, don't worry. Breathe in, breathe out. We're good. But I want you guys to put these ones in parentheses. They're not used very often. Like, you can. But you don't usually make a sine something harder. Sine is 1 over cosecant. Like, why would you do that? I like sine. I know, so do I. Like, put these ones in parentheses. They're true. They're just kind of gross. And these ones, you did already write down cosecant is 1 over y. And some of you, the unit circle with the xy is working, at least kind of. You just have to study it more. We'll do some more unit circle practice at the end of class today to see how it's going. But you can't just stop with the x and the y. You do need to know that cosecant of theta is 1 over sine of theta, or cosecant of x is 1 over sine of x, or cosecant of t is 1 over sine of t. These variables can change, but the identity remains the same. Quotient ones, tangent is sine over cosine. Wait, we know that, because y over x. Oh, cotangent, x over y, cosine over sine, etc., etc. Pythagorean, now that gets interesting. Pythagorean identities get interesting, and that's kind of what I want to harp on for just a second. We're going to come down here to the note, but first of all, Pythagorean, isn't that a right triangle thing? Right? A squared plus b squared is? Now, how does that correspond to sine and cosine? What if I was to draw the first quadrant of the unit circle? True? And what if I was to mark some arbitrary point? Yeah, you could say it's pi over 3, but maybe it's not. Maybe it's something a little bit off. And that point has an x and a y. Now, what did we say last section? Section 4.2, the unit circle. What did we say went together with x? Who is x? What trig function? Do you guys agree? Cosine? I heard that from a few. Good. X is cosine, and then y is sine. So if x is cosine of a certain angle, and if y is sine of a certain angle, then what happens if I draw not just a line to the angle, but a right triangle to the point? What if I don't just draw a line to the angle like we did in the unit circle? You guys just drew to like pi over 3 and pi over 4 and pi over 6 and blah, 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 right? What if you didn't just draw a line to the point, but also a triangle? And the triangle, if you go over, isn't the over x? And isn't the up y to any point? Go over x and go up y. Couldn't we say then that x and y and 1 would be the labels for my right triangle? True? So Pythagorean theorem says x squared plus y squared is 1. And what did you guys just tell me was x? And what did you just tell me was y? So technically we could say substitution would get us cosine squared plus sine squared of thetas equal 1. But guess what? There's a spiffy notation with trig that says, hey, all of cosine squared, all of sine squared, it can be rewritten as sine squared theta plus cosine squared theta equals 1. This is a shortcut notation to the big old whole thing squared. Now, some of you are like, no, it needs to be the other way around. Addition's commutative. It doesn't matter. It doesn't matter. Cosine squared plus sine squared plus cosine squared. It all equals 1 because it all comes back to Pythagorean theorem, triangle in a unit circle. True. A right triangle in a unit circle true. So the Pythagorean identities, technically, this little guy right here comes from, bless you, this little guy comes from this illustration. Why is it called Pythagorean? Because it literally is. Why is it called Pythagorean? Because it literally is. Coming from a right triangle in the unit circle. Now, that's the first one. We're going to look at the other two in just a second as to where they come from, or maybe we'll wait and do that another day when we have a little more time. But here's a question. Using this table, is there a way that we could or fill in for just what sine squared of theta equals? Either using a formula directly or maybe rearranging some formulas. Does anybody have something from the table that could substitute, represent, equal sine squared of theta? 1 minus, I like it. Do you guys agree with Salma? That was you, right? Can we rearrange the Pythagorean and subtract cosine squared? Yeah. Sine squared equals, take that guy away. All right, that's true. Does anybody have anything else sine squared could equal?
1 over cosine squared.
You could change the sign for 1 over, oh, wait. There's shortcut notation for trig. I can just write it like this. You can substitute sine for 1 over cosecant and square it. Oh, wait. You can make that nice. 1 over cosecant squared. That's true. Does anybody have any other ways that we could write sine squared? You have to be creative for the next one. What did Jason rearrange? Yeah, the quotient property for tangent. He said, well, I can multiply up the cosine to get sine and then square that, which would be tangent squared cosine squared. Remember, if you square trig, you can make it these nice little notations. You can go backwards or forwards with those notations. Example, I know. Whew, wow. If you were to have something like cosine squared of 12 degrees, you're like, that's not unit circle. I don't know what the number is. How would you put it in your calculator? Can I go ahead and just quickly, just to make sure we know what's going on? If I was to insert a page, because we might be using our calculator a little bit in this section, if I was to ask you really quickly for cosine squared of 12 degrees, how could you do that in your calculator? But try to do it. Can you do cosine with a squared before the parenthesis? No, it puts the parenthesis in. You're stuck. Now you can try cosine squared and then a parenthesis and have a couple parentheses. Does it work? Okay, hold on. Why are our calculators not open? Chris and Lauren, get your calculators open. Come on. How would you do it? You guys like your calculators. You like calculator questions. There's no way to do this guy by hand. How would you put in cosine squared of 12 degrees? First of all, what mode should you be? Radians or degrees? Okay, so pause. Double check you're in degree mode. But we're struggling through, and you guys are struggling. Here I am. I'll struggle too. Or at least pretend to struggle. I kind of do that a lot. I'm in degree mode. Actually, I'm not sure if I am. I am in degree mode. You guys see what I'm talking about, right? How do you do the squared? Squared? 12? Does that work? Well, how do you do cosine squared of 12 degrees?
144.
But who's being squared, the 12 or the cosine? Come on, someone has an idea. How do I square this? Cosine of 1 over 12. The whole thing squared?
I have no idea.
Pause. What did I just say on the page before? If you square, right? I can zoom in real quick. If you square a cosine, there's a shortcut notation. The problems will give you the shortcut notation, but don't forget where it came from. trigonometry, when it's squared, when trig functions are squared or cubed or to the fourth or fifth or sixth or square rooted, you need to do it to the entire function, but it won't look like this. This is messy. There's a shortcut notation. I say don't get tricked by the trig notation. Don't get tricked. This squared isn't meant to be right next to the cosine. It's actually meant to be around the whole cosine. So one way is to do cosine of 12, the whole thing squared. The other way is to make sure that we're right. Guys, isn't it when it's squared, it's times itself? We could have been spiffy and just done it that way too. Should be the same thing. Ha ha! Dun 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 dun. Matthew. Over the 12? Well, But here's my question. Did you know exactly what that meant? Meaning, do you understand why that is not the same as cosine 144? I'm not sure every student knows that's not the same as cosine of 144. I think a lot of kids would think that means cosine of 144. So therefore, in order to show everyone the idea of what's going on and to prepare you for something kind of tricky in calculus, I would say, even though this is a shortcut because your calculator knows that you're saying beginning of cosine, ending of cosine, I'm done with cosine, now square. Even though your calculator actually knows what you mean, I'm afraid a few kids would plug in like a 12 squared as this and get the wrong answer. Does that make sense? That does not mean cosine of 144, so make sure that you know what your calculator is doing when you plug in things. But long story short, when you have cosine squared of, what does it actually mean? It doesn't mean cosine of 144. It means cosine of 12 times cosine of 12, or cosine of 12 squared. Okay? With that, let's go ahead and see, why did we cover all of these formulas? Is it really just to be able to put something in our calculator? No. It was to deal with nasty things like this that could be rewritten like this, saying, you know what, in just a little while, a chapter or two, we're going to have equations with nasty stuff like that we won't be able to solve for theta or solve for x if they're stuck inside unless we make it simpler. And so these formulas, even though we're not going to totally understand it today, you're just being introduced to these formulas to say, hey, it could be helpful in the unit circle to know that cosecant is 1 over sine. Because if your brain knows, I know sine, cool, cosecant says take it and flip it without using the whole xy table. There are properties that are way bigger than the whole xy table of xy formulas that we learned in section 4.2. So we're going to practice using those formulas just a little bit, but also apply them to the unit circle at the end. So here we go, number 47. Number 47. I want you guys, as you write this down, to think back to geometry proofs. To think back to geometry proofs. 2-column proofs. In one column, you wrote the given. I should say in one step. In one step, you wrote the given. And what were you trying to get to at the very end? Every question gave you a given and it gave you a proof. Good. It gave you a given and it gave you a proof. Up here, I know it's not that bad. Thanks, Matthew. Don't worry, they get way worse. Just not this section. So let's enjoy the simple ones, and then we'll work together on the hard ones. However, pause. I need all of us just take a second, and remember, this class is not just about you. It's about all of you, and all of us trying to get to a common goal together. So here we go. As we look at this, I want you guys to actually write given and prove. This is not going to literally be shown in a problem. This is not going to be literally shown in a problem. And this is a super basic one. And in just a few sections, you're going to be like, oh, please give me this one on the test. This is a super basic one. But I'm teaching you the process with a basic one, like almost every teacher does. So given and then prove. When you were in geometry and there was a given and there was a prove, were you allowed to start playing with the given and then randomly just start writing about the prove, and then go back to the given a little bit, and then go back to the prove a little bit, and then end somewhere in the middle? No. You were supposed to go like in a linear progression of from the given to the prove. Now, did that mean that you weren't allowed to think about the prove a little bit? And be like, what could have been the step before the prove? So if the triangles are congruent, maybe it came from the picture. It looks like an SAS sort of thing. So maybe I need to get down to the SAS and then I can prove. Sometimes you would think backwards and forwards, but your proof had to go in one direction. Same thing here. What do I mean? Even though the book and the calc chat might look weird, what you need to do or to prove this properly in preparation for harder ones is to take the given and just play with him and make him match the proof. You can't go working back and forth, meaning we can't go multiplying and dividing to the other side. It's actually illegal. You can't go multiplying and dividing by the other side. You need to take the given and work with the given. Now, sometimes these change. Sometimes they write them in weird orders, or sometimes both sides are kind of tricky. So you could work from this given to this prove, or this given to this prove. You can make it what you want it. Which one's the given, which one's the prove. But in this one, it's pretty obvious. The left one is the one I can play more with. And I can play with them by looking at the properties. So you guys have all these properties on the page before. I know some of your brains already jumped straight to, of course that's true. Great. I love that you got to, of course that's true. But what I need you guys to think about is why. So y is tangent times cotangent 1. Can you give me an identity or a property that I can plug in that would get me to 1? The cotangent? Which one? Reciprocal or quotient? There are two. Okay, so if I was to use the reciprocal formula for cotangent, I could substitute for cotangent 1 over tangent of theta. So I could use an identity and then use math, because math tells me, what's tangent over tangent? What's anything over itself? Nice. So I can say, oh, hey, I made the given match the prove. Dun, 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 dun. Check mark says you're done. Well, on this one, it was super nice and basic. Now, was there another way to do it, though? Yeah. What if you had, instead of going this direction, what if you had gone using the quotient property? Could I have also used quotient properties? And said that tangent is sine over cosine? And cotangent is cosine over sine? Doesn't math then tell me, oh, reduce, 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 1? There is sometimes more than one way to get there. And some of your brains are going to think very differently. And sometimes one way is longer. Technically, there were 2 substitutions instead of 1. Sometimes some of your brains will take the longer way. And it'll be headed towards the right direction if you just persevere. Some of you will head a wrong way, and you're just going to keep on getting more and more wrong as you go until you come back and reevaluate. And some of you will, every now and then, choose the easy way. But sometimes there isn't an easy way. What am I building up to? How about this guy? Pause. Breathe. It's not that much harder. Joe is saying distribute. He's saying start with math. This one, we actually started with identities, then we did math. Joe's saying distribute, start with math, and then make identities. Or we could start with identities and then go to math. Both ways are accurate. Both ways will eventually get you there. Did anybody else, though, look at this and think, I should FOIL? Okay. Okay, so I'm going to go ahead and go the math way first. But for any of you that were like, secant is 1 over cosine and tangent is sine over cosine and secant is, you could have gone that way too. But just because most of our brains thought FOIL, I'm going to go that way. This is our given, if you guys can't tell. We don't know what to do with 1. That can come from a million, infinitely many different places. So, distribute. What's secant times secant? Yeah, and I'm going to use the cool, nifty shortcut notation. Is that okay? Secant squared of theta. Outer, you don't like it, but it's true. Negative secant of theta, tangent of theta. Inner, secant of theta, tangent of theta. You know what? I'm going to be devil's advocate. Some of you would have written tangent secant, and it might have confused you, so let me write it. Tangent theta, secant theta, minus tangent squared of theta. That would be last. Secant squared minus secant tangent plus tangent secant minus tangent squared. Oh man, that's not 1. Yeah. Even if one's secant tangent and the other's tangent secant, xy and yx, they're the same thing. Did anybody notice this was a difference of squares to begin with? And a plus b times a minus b is a squared minus b squared. You could have done a shortcut to get there. But either way, we're here at secant squared minus tangent. Many different ways we could go. We could use the reciprocal properties. We could use the quotient properties. We could use the Pythagorean properties. Sorry, I'm saying properties, identities. What do you guys want to use? Give me a name. Reciprocal. Yeah? But how are we going to use it? What do you guys want to substitute for? The secant squared, the tangent squared, or the secant squared minus tangent squared? Can we do all of it, or do we have to do it? Yeah, I would just do a piece too. Which piece do you want? I like secant squared because isn't it already by itself? It's already by itself. What does secant squared equal? Check it out. Oh, did you write it down? 1 plus tangent squared. Oh. Do you have your phone, Jordan? I'll take a picture of it and bring it to you. Really? Oh, this will be fun. 1, 2, 3. There you go. Happy birthday. Hey, if they can do it at the Grammys, I can do it here. So, that was a fun year. That was when they brought in like all the pizza and everything for the people in the front row. Oh, was it the Oscars? I don't remember. It was hilarious though. Was it the Oscars? I was like, I want to be there. That looks fun. Like actually fun. Usually I'm like, that looks boring. Okay, tangent squared minus tangent squared. Ha! Dun 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 dun.
Wait, where did the secret go?
Oh, look at your formulas. Pythagorean, the second one down. 1 plus tangent squared can replace secant squared.
Oh, so it turns into
Substitution. Yeah. Yeah. Jason.
Couldn't you have just moved the negative tangent squared to the other side and said secant squared equals tangent squared?
But that would have been playing with the given and the proof.
Oh, I see.
See what I mean? So as far as the structure and the procedure, it's illegal.
Wait, okay, so 1 plus.
So it's substitution. I take out the secant squared, and I plug in 1 plus tangent squared for it because of the formula.
And then that was already functional. Okay, I see it.
Yeah. Sorry, that was a minus.
Okay, so I didn't see it.
That looks funny. It looks like times now. There we go. Is that good?
Yeah.
Cool. Guys, you're going to see a couple more in homework. Maybe some of them will be super basics. Maybe some of them will be a little bit harder. You have a choice, and these two show 2 different ways. One says go straight to plugging in, and hopefully the math will work. The other one says go straight to the math, and then hopefully the plugging in will work. If you try one way and it's not working for you, you could always go back and try the other way and say, well, maybe instead of distributing, maybe I should have done plugging in right away. But don't worry, we're going to be talking about this a lot more in a very, well, in a much more formal setting. This is kind of like, hey, there are these formulas. So it's not just that cosecant is 1 over wherever cosecant is. It's not just that cosecant is 1 over y. He's actually 1 over sine all the time. So it was just an introduction, seeing these formulas and playing with them just a little bit outside of the realm of unit circle. But we have to come back to something because this section is called right triangle problems. So maybe we should do some right triangle problems. Oh, come on. You're fine. I let you get out your calculator. I agree, but we can't really get back to it until chapter 5. You have to hang in there. But don't worry, Matthew, when we get back to it, we get back to it. Good. All right. It'll be fun. I think it was Sean Durkin 2 years ago. 2 years ago? He worked and he worked and he worked on a particular homework problem, and finally he got a proof. I think he came in, he was so proud of that thing. He was like, man, The whole page. He was stoked. No, it was right. The poor kid, though. The poor kid, though. He went this direction. And I was like, or crushed his dreams. But at the same time, he got it right. Like, he got it right. He did legal steps all along the way. It took him a long time to figure out. Multiple hours, if I remember right. Not all at once. There were definitely some snacks in between. Honors Precalc. But here's the point. There was a simpler way. Maybe he should have stopped and reevaluated. And I think he did a few times. But he kept on making legal steps, and he eventually got there. I don't remember if it was a half page or a whole page, but it was a lot of his little tiny writing. And he was so stoked. And he was right. There was just a faster way. So when you guys get there, you have to be willing not to be discouraged because someone else might do it another way that's easier than you. Ooh, there's definitely a life lesson in here somewhere. Because you're going to figure out how to do it, hopefully, a way that works in your brain. And there are multiple ways. It's going to take some perseverance, some grit. But for my puzzle people, it will be fun at times. Mrs. Regan, when her daughter, Katie didn't take Precalc. Danny did. Mrs. Regan loved T-proofs, is what you call them. Trigonometric proofs. She would beg Danny to do her homework. Of course, Danny loved doing it too, so said no. But she's like, if anybody ever wants help on T-proofs, send them my way. I love them. It's the one thing that she remembered from Precalc. But that's chapter 5. Although I doubt it was called Precalc when she took it. Vectors. Vectors, chapter 6.
What's the voice?
Probably chapter 6.
You have your script from one of the calc. I don't remember if it's A, B, or B, C, but it says don't shrink and go around.
That was George Corey's year.
Oh,
Yeah. Big George.
Oh, that was
All right. Deriving is a calculus thing. Okay, now that we've been thoroughly distracted. So that whole trig thing, Matthew, long story short, they're coming back. Just wait. And you have some in homework. Have fun. If you guys see something called angle of elevation, remember, elevation, you're looking up. Angle of depression, you're feeling down. Just kidding, you're looking down. Well, same thing, right? Angle of depression is going measuring down, angle of elevation, measuring up. It's something that's kind of confusing, especially if you have something like, here's a person, and here's a plane. I'm just writing the word plane because you guys will make fun of my picture. And if we're talking about an angle of elevation to the plane, we're talking about person to plane from ground, the angle up, right? But if we're talking about somebody in the plane looking down at the person because they could see them, angle of depression, that would be looking down from the plane. And it's not always like a picture where there are actual lines like the ground or going through the air, the line would go down from that, or the person's line of sight if they look straight out the window versus looking down towards the ground. Now, every now and then, the angle of depression and the angle of elevation will be congruent. Oh my goodness, parallel lines, alternate interior angles. Anyway, sorry, too much geometry. Let's go play with what kinds of problems you might see. Oh my goodness, there aren't even words. Well, they want us to solve for what's unknown. What's unknown? Well, kind of the whole triangle. I mean, don't we technically know that if that's 60 and that's 90, we know this is 30? I mean, kind of know that. Who's X? Who's Y? Who are the things or the parts or the pieces that have been labeled as an unknown variable? Oh, wait, we like right triangles because x squared plus y squared equals 18 squared. And you are stuck because there's nothing to do to solve for x or y. Does Pythagorean always work? No. So why would solving right triangle problems show up right after we first started going through trigonometry? Because SOHCAHTOA, each trig function only needs 2 sides, not 3. Pythagorean needs all 3 and we're in trouble. Trig only needs 2 sides. Now, I think if we use tangent, we're probably in a bit of a pickle because tangent would say, hey, opposite over, oh, we still have 2 variables. Forget tangent. But who is a good idea? He's great. Because sine of 60 degrees is equal to, you guys tell me the ratio. So, opposite over hypotenuse. Isn't there just one variable in this expression? Nice. Can't we just multiply the 18 on the other side? Now, I'm not going to totally finish that problem yet. I'm just going to ask you, first of all, we have a way of solving for y, so how could we solve for x? Cosine. All we want is some sort of expression, some sort of formula that has only one variable. Trig only needs two sides. Use the hypotenuse, and then you'll have your other side ready to be solved for. I'm not saying you should always ignore Pythagorean theorems. Sometimes it's great. But sometimes it's just frankly not gonna be enough. Now, I told you guys to get out your calculators because some of the angles in homework might be things like 12 degrees, which you should or have no way of totally knowing what that is precisely. You could maybe make a guess. I could maybe make a guess, an approximation. And some of you might be going to your calculator right now, but why, oh why, you guys, that you should be able just to go what's so special about 60 degrees? It's on the unit circle. This could be on a non-calculator quiz or test. And a multiple choice answer might not have it written out. It might be solved for. And the only way that you could make it match is if you knew your unit circle. How did I figure out that sine of 60 and cosine of 60 is, root 3 over 2 and 1/2 in order to plug in? Don't worry, I'm coming back to it. Many different ways. To be honest, in my head, what I literally did was think about 60 degrees, 1/3 of a pi, 1/3 of a calzone, and I thought of a triangle. I thought of a, hey, I would go up a lot and I would go over a little. Now, some of you don't think about that. Some of you are liking the xy from section 4.2. You're like, I can do this way. Cool. If you can do the xy way, that's cool. But I actually think of it as a triangle, and I think of all the different ratios. Well, I guess I kind of just have them at the ready in my head as to what the special numbers could be. And I think of my 3 in the middle, which are the tricky ones. 0 and 1s are on the axes. I kind of think of them on their own. But I think of this one as being a little, this one as being a lot, and this one as being, I don't know, the middle? You can think of Goldilocks if you want. But I have the little, I have the lot, and I have the middle. Just right. How do I get to this triangle? I go over a little, I go up a lot. Ha-ha! My little is cosine, adjacent. My lot is sine, opposite. So I threw in my sine, I threw in my cosine, I knew what it was, and I solved. Others of you using triangles for the unit circle, I said I would bring it all back together. Others of you might, with the 60 degrees, hopefully we all could get here-ish. Are we okay getting 60 degrees first quadrant, not 90? Others of you might be like, wait, 60 degrees, that's a special triangle from geometry. I might have to go outside the unit circle, but whatever, root 3, 2, 1. Maybe you wouldn't have done the scale back triangle of a little and a lot, the nice little trig ratios. Maybe you just rather keep the geometry triangle, 1, 2, root 3, and say, oh, well, if it's 60, that's easy. Opposite over hypotenuse is sine. Adjacent over hypotenuse is cosine. Dun, 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 dun. But once again, maybe just a couple of you are like, can you just... Y is sine. Is that? Yeah. So we have our little unit circle with x's and y's. We have our little scale back triangles with littles and lots for my visual people moving around the unit circle. And then we have our big triangle way for our geometric people that are like, you know what, I know this thing, I'll just use him to get whatever trig function I want. We're going to get back to the unit circle in just 1 second. For right now, let's do one last section right triangle trigonometry problem. What if they said a surveyor is standing 115 feet from the base of the Washington Monument, as shown in the figure below? The surveyor measures the angle of elevation to the top of the monument. Oh my goodness, they gave you a picture. Spoiled rotten. 78.3. You need your calculators. We can't do that in our head. That's not unit circle. How tall is the Washington Monument? What are they asking for? And specifically in context of the triangle, the opposite, you guys agree? There's the monument, there's the surveyor. I know I'm exaggerating the picture, but there we go. 115. 78.3. And I want my opposite. So what trig function, cool kids? Pause. Everybody stand up, give a high five to someone, turn around twice, and sit back down. Pause. Stand up. Give someone a high five. Make their day. Say happy Thursday, almost Friday, almost weekend. Give a little bit of hope. Share the hope. Sit back down. But wait, before you sit down, ask them, what trig function should we use? All right, as you sit back down, what trig function should you use? What do you think? Sine. Okay.
No.
Playing devil's advocate. I heard sine. Sine. Opposite. Great. Lauren.
Tangent.
Won't you just let me even get to the point where you tell me I'm wrong? Sine. Opposite over. Oh, I don't know him. Which is why we have to use tangent, which is opposite over. I do know him. Okay, go solve. If you don't need me, then go solve for it. But I'm glad you don't need me. Go solve for it. Calculator, degree mode, double check with someone in your group. I don't have my calculator, so I'm depending on you guys to get me a good answer when I ask for it in just about a minute. Was it too hard to get y by itself as soon as you use tangent? Nope. Because, unlike some other problems, this one just needed a simple multiplication, right? And as long as you were in degree mode, all of your answers should match, even though I did not hear really any checking with your group member like you were supposed to. But what did you guys end up getting? You guys agreeing so far? 72 point what? Oh, is it even? Give me like 3 decimals. 2. What's the next decimal? We should always be rounding the same as we need to. So Matthew, give me 4 decimals. What is it? 32. Sorry. 3236, right?
I got like 555.
Looking at the picture, yeah, it looks kind of weird. I was going to go for it, though. So what did we get? Point.
314.
Okay, careful in math. When you round, there is a very specific way to round. Look at the decimal place right after. If it's 5 or above, you round up. If it's 4 or below, you round down. We have to be precise. Feet. Okay, unit circle time. Back to your homework spiral. Ooh, why does it say 25 and 26? That's weird. I'm going to pull up your homework sheet at the same time because that's weird. But unit circle practice. Could you use the circle? Sure, you could try. Could you try to maybe play with some triangles? Sure, you could try, but you got to have a way that works. And does having your unit circle open and just kind of like looking work? No, not for the quiz anyway. Let's see if you do any better on the 3 today. Ready? Unit circle, pop quiz? Yeah, but it's in your homework spiral. I'm not grading it yet. Ooh. This is for you, yourself, and you. This class is not just about you, it's about others. Do the best you can without your calculator to fill in these 3 values. Does anybody figure out this is 1 1/3, aka third quadrant? Cosine is the adjacent, aka the x, aka a little. This guy, but he's negative because he's in the third quadrant. Did anybody figure out 3 pi over 4? That's almost a whole calzone. Sine, that's the opposite. Oh wait, the over 4s are the same number anyway. Root 2 over 2, but in the second quadrant, all students. Sine's positive. And this last one, cosecant, oh my goodness, he's 1 over sine using a property by Jason from, or an identity from the lesson. 11 pi over 6, isn't that almost 12 slices, aka 2 pi? Sine is the opposite. Opposite is the little one. The little one is negative 1/2 negative because all students take cosines positive, not sine, or you're going down. And when you flip, now pause. Some of you are like the triangle thing and the circle thing are not working. There is one other way. And I want you guys to tell me go when it hits the 9. Ready?
Go.
Wait. You could write this at the beginning of any quiz, any test, any SAT, and refer to it. See you guys tomorrow. Bye. Took me what, 15 seconds? Maybe 30. Yeah, you can take a picture. There's a song that goes with it. 1, 2, 3. 3, 2, 1. All over. Square root of 3 over 3. 1 square root of 3. Of course. Take cupcakes to your friends. We're just trying to get rid of them. Good call, Tyler. I bet she'd be a fan.